All right, I think it's time. Last time we learned about the determinant of A. This was determinant. It wasn't just last time. First what we did was we did the 2 by 2 matrix case, and we actually found the whole inverse of that matrix. Along the way we discovered this thing called determinant, and then we've been spending a little bit of time looking at determinants of larger matrices, and we finally got a determinant definition, and you can write it out in words. It's a little cumbersome. The simple way to describe it is what's called cofactor expansion along any row or column. And I'll remind you what a cofactor is. Cofactor is Cij, which is -1 to the I plus j, Mij. And then Mij was this whole other determinant of a smaller matrix. This was the thing where you crossed off a row and a column, and then you had some leftover numbers. You took the determinant of that. So you can go back and look at your notes, but this is just an overview. The cofactor expansion, what that means is I take the elements of the row or column that I choose, and I multiply each one by its corresponding cofactor, and then I add them all up. So we had a few examples. We did a 3 by 3, and we did it 2 different ways using a row and a column. Now we're going to build on that and do a 4 by 4. So we'll start simple, and then we'll have it grow a little bit. So first of all, it's just kind of intimidating that it's a 4 by 4 matrix. There's a lot of numbers in there. Since we can choose any row or column, it's going to be preferable that our row or column that we choose has as many zeros as possible. Because what are we going to do? If I choose, let's say I pick this row right here. Well, then what am I going to do? I'm going to take 1 times its cofactor plus 2 times its cofactor plus -1 times its cofactor. Well, that means 3 computations. Whereas if I choose, instead of doing that, let's say I choose this column here, well, then there's only 1 computation. I'm going to do 0 times whatever its cofactor is, but I don't need to compute the cofactor because I'm going to multiply it by 0. It's not going to matter. Then I'm going to have this -1 times its cofactor, and then 0 times the other cofactor, so those aren't going to show up. So this is the smallest amount of computations that we can achieve here, having a single column with 1 non-zero entry. By the way, I could have also chosen that third row there. That would have been just as fine, but I happened to pick the column here. Okay, so then the other thing I need to make sure I keep track of is the pluses and minuses. Remember last time we talked about when you compute the cofactor, it's got this -1 to the end, so it's better if you just keep track of that in your mind. So let's just do the whole matrix here. You don't even have to do the whole thing. When you're doing it, you just want to maybe refer to it a little bit. It always starts with a plus in the upper left-hand corner because that means 1 plus 1, so it's even. -1 squared is positive. Then it just alternates from there. So if I just keep track of this while I pick the different elements here, in fact, when you're doing this in practice, what you might do is once you pick your column, just go and put down the positive negatives next to it. It's just to remind yourself. So it's going to be plus, minus, plus, minus. That's the column that I'm doing. So I could put a little plus, minus there if you like. I'm just showing you little tricks that you might develop as you do more of these, just to shorten things up. Okay, so the determinant of A in this case, it's going to be 0 times its cofactor, but that's not going to show up, so I'm not going to write it. Then I'm going to have -1 times its cofactor. Let's just write it out for just for practice. What is the cofactor here? It's in the second row, third column. So I could write it like that. C23. It's not necessary that you write this step, but for practice we'll just do it this way. Okay, so that's equal to negative 1 times, now I'm going to write out what the cofactor is, that's negative 1 to the 2 plus 3 times M23. Now this is what I was saying over here, you don't have to write this out. If you just realize it's a negative, you just cancel the negatives essentially. Okay, so let's write out what this is. M23, so this is just equal to M23 because I have negative 1 times negative 1. Now let's write out what M23 is. M23, it looks like it's a matrix because of the notation, but what you have to realize, it's the determinant of a matrix. It's not just a matrix. So I can use the straight bracket notation, compare that with the original matrix where I used the regular brackets. Okay, and then M23 means I'm going to take the determinant of the matrix where I remove the second row and the third column. And then, so if you like, you can write it all out, but I'm not going to. For a 4x4, it's a lot of work. Maybe I'll do that for the notes anyway. It's just one extra step. So M23 is the whole matrix 1, 0, 0, 1, 1, 2, negative 1, 0, 0, negative 1, 0, 0, negative 1, 0, 0, 1. It's always dangerous copying these things. You can lose some information. Okay, so M23 is not this. It's the determinant of that matrix where I've removed the second row and the third column. So that's the same as saying it's equivalent to this 3x3 matrix, 1, 0, 1, 0, negative 1, 0, negative 1, 0, 1. Okay, now we have to take the determinant of this 3x3 matrix, but you see we have the luxury of picking a row or a column, so I'm going to pick once again the one that makes the fewest amount of computations. Here I have two choices, it seems. I could either pick the column here that has only that negative 1 in it, or I could pick that row. I'll just pick the column here. Just practice. Okay, so let's write that out. When I do the cofactor expansion for this determinant, I'm going to multiply by this. It's negative 1. Now, in this configuration, that's a positive location. If you want to put up the plus minus thing, you can see that this negative 1 occurs in a positive slot. So this is equal to negative 1 times negative 1 to the 2 plus 2, M22, which is equal to negative. M22 means I cross off the second row and the second column. So I get 1, 1, negative 1, 1. So that's equal to negative. I have 1 plus 1 is 2, so negative 2. That's the completion of that determinant. So good news and bad news. I mean, when you have a 4x4 matrix, typically if you're going to be asked to do one, I'm not going to give you one that's got a bunch of columns, you know, in rows with zeros in it. You're going to have to achieve that yourself. But that's reducing it down to the smallest amount of computations we can get right here. I didn't have to do much, even though I had a 4x4. So the next level would be to give you a more complicated 4x4, and we're going to start to use some of those theorems that we went over last time, one in particular. So here's my new matrix A. It's going to be bigger and messier. It's 4, 2, 1, 1. I want to get the determinant of this. Don't just jump right in with these things. Pause and look at it for a second and try to figure out your best course of action. So since I have some experience, I can try to share that with you. So when I see this, I say, I'm looking for as many zeros as possible. The best I could do is, this is probably the best column I could get. I know there's this column with a 0, and I know there's that row with a 0, but those have 2's in them, and I'd rather have 1's than 2's. So I see that as being the best column, but I don't want to just jump right in and start finding the determinant, because that's going to require me to do 3 different 3 by 3 matrices as I do the cofactor expansion. So what I'd like to do first is do some row operations. If you recall, theorem here 9.5. Theorem 9.5 says I can do row operations of the normal type that we've been doing, where I take a multiple of a row and add it to another row. Theorem 9.5 says this doesn't change the determinant. So I might as well take a step to do some row reduction to get myself into that situation where I have a single non-zero thing and then 3 zeros. So let's get that. It won't take us much. We have to do 2 row operations just to get rid of those ones right there. So what am I going to do? I'm going to replace row 2 with negative row 1 plus row 2. Let's start to fill those things in. The top row is not going to change, so just reproduce it. The second row is going to change, so what's it going to change by? I'm multiplying the top row by negative 1, so I get negative 5 in the first spot. Then I'm multiplying this by negative 1 and add it, I get negative 3. Then 0 here by design. And then I'm going to do negative 1 plus 2 gives me 1. So that's the second row. And then I also want to modify this one right here. So I'll do replace row 3 with negative row 1 plus row 3. Okay, when I do negative here, I get negative 4 plus negative 2 is negative 6. Negative 2 and 0 gives me negative 2. Negative 1 and 1 is 0. Negative 1 and 2 is 1. Okay, that takes care of the 2 rows I was interested in modifying. Now I'm just going to reproduce that 4th row. So the nice thing about doing all that work is that the determinant of this matrix is the same as the determinant of that matrix. So when I want to compute the determinant of A, I might as well use this one. I mean, which would you prefer? This has got the column with 3 zeros in it, which just makes only one matrix that I really have to do the determinant of. Okay, now just for your practice, since this is the only guy that I'm really going to use, let's just go and get the plus minuses. So it's plus minus plus. That's a plus location for the cofactor. So this determinant is equal to 1 times the C13 cofactor. I don't need any of the others to be present. And that's going to be equal to the determinant of the matrix negative 5, negative 3, 1. Then negative 6, negative 2, 1. Then 1, 2, 1. So that original matrix, it's the same as just computing the determinant of this. For this one, you could also do row reduction for this one too if you like, but for 3 by 3s, everything reduces down to 2 by 2, so you might as well just go for it here. It's good practice. Anyway, okay, so let's put our pluses and minuses in. This is a plus, then minus, then plus, and then this one's going to, so I have plus, minus, plus. So see if you can follow this determinant here. Let me make sure I have everything, at least the way I have it in my notes. Yep. Okay, so I'm going to go down this third column here. It's going to be 1 times the matrix left over once I eliminate the row and the column that 1 is in. So I have a negative 6, negative 2, 1, 2. And then the next one here, this guy right here, this is going to be minus 1. That's from the cofactor. So if you like, this minus is right there. That's why it's a minus, not a plus. Okay, I'm operating on this one right here. I'm going to cross off its row and its column, and what I have left over is negative 5, negative 3, 1, 2. And then the last one, this is a positive location, no need to modify it. It's 1 times the determinant of negative 5, negative 3, negative 6, negative 2. Okay, I've got negative 12 plus 2. And then here I've got minus negative 10 plus 3. And then there I've got plus, that was a negative 2, right? Yeah, so positive 10 minus 18. So this gives me negative 10 plus 7 minus 8. So negative 11. That's the determinant of that original 4 by 4 matrix. Yes?
Are you getting the negative 2 plus 2
These here?
Yeah.
Okay, so I'm computing this determinant here. So it's negative 12. It's negative 6 times 2 is negative 12 minus negative 2 times 1. So it's minus negative 2, which gives me plus 2. And remember that the determinant of A, B, C, D is equal to AD minus BC. That's the determinant of a 2 by 2. All these determinants end up boiling down to determinants of 2 by 2s if you want them to. Yes?
Instead of finding the cofactor, after you remove the ith row and the jth column on the first part of it, and you end up with a 3 by 3, could you do that again? Get rid of an ith row and a j column and just find determinant like that?
You mean reduce it more with row operations? Yeah. So, but actually, I'm a little worried about the way you said that. I would remove, if I understand you correctly, you want to use that to make some zeros first? Like the way we did that in the first step?
No, I was going to say just remove one row, one column, and then you're left with a 3 by 3, then get rid of another row in the column, and you're left with a 2 by 2, and then you...
No, we're not just getting rid of rows. What we did was we created zeros, and then that allowed us to have only one 3 by 3 matrix. If I didn't have those zeros, I would have gotten 3 3 by 3 matrices to do. So that step up there is to create those zeros so that I only get one. So it's not like I just crossed off something and created that. Yeah, that was the row reduction that I did. And we used that theorem to justify it, that step. So that's a good one to practice. Okay, you can even just pick other rows or something. You know what the answer is, so you can just keep doing. You can get a lot of mileage out of just one matrix by just picking different rows and manipulating it differently, and you should always get that answer. So that's a good, efficient way of studying. We went through all those theorems last time. So what I want to do is I want to do a couple of proofs that require those theorems while they're still relatively recent in your notes. Here's a couple. Remember, these are exercises that are in the book that I've assigned or suggested. But I want to do them for you because I don't want to assume that you know how to do proof writing. So I'll just write out a few proofs. There's a couple of proofs. There's 3 proofs that you're going to be responsible for. I've given you one of them already, and then the 2 I'm about to do are the other 2. So then you'll have a complete list of the 3 proofs that I might put on the midterm. And you go and you learn these. Okay, so it's good. They're good ones to practice with, just to learn proof writing technique. Okay, I want to prove this statement. So if you were to get this problem yourself, and it is in the book, so maybe you've already tried it, what you would do is you would have to thumb through the book and find some theorems or some facts or things that are related to this. And even if you don't really understand it, you're just looking for theorems that involve this symbolism. Symbolism like vertical lines and capital letters. You just look through the theorems. Are there any theorems that have capital letters and vertical lines? And there are. So the one that might stand out to you when you're looking through them is theorem 9.8, which says that the determinant of AB is equal to the determinant of A, determinant of B. So at least you found some kind of fact that looks like the thing you're trying to prove. That doesn't mean you've hit a home run, but at least that's what you would start doing. Okay, you start collecting facts that look similar to what we're trying to prove. All right, and then we have to just kind of follow our nose. So I need to start with the left side, and then I need to do a series of logical steps and have my last step be this. And each one has to be justified. Okay, well, this theorem allows me to at least say something about this. It allows me to break it up. Okay, the area here is equal to the area of the first one times the area of the second one. That's what we kind of looked at. Or the determinant and area are interchangeable terms. So let's split that up. My goal is to have this. Now you might realize, wait a second. Couldn't I also say that, isn't this true? It doesn't really matter. That's what you really gain from this, is to understand that, okay, A and B, these are just dummy variables. It just means I have a matrix times a matrix equals the determinant of this matrix times the determinant of that. So if I just happen to call this one B first and this A, it's still true. Right? It doesn't matter that I called them A and B. I can have, I could have Mickey Mouse and Batman. Right? Then that means that's Mickey Mouse and Batman. It doesn't matter. So since I'm headed towards this, I'd like the step right before that to be this, because then I can justify it. So let's do some justification here. Here I would say this is just a straight use of theorem 9.8. But then what about this? Is this justified? How do I switch these two? How can I justify that? What's that? What's going on there? What is a determinant? If it's the area, what else? What is it? It's just a number, right? Isn't it just like a 5 or a 7? Right? It's just an area. It's just a number. So with regular numbers, we can switch things. If I have 5 times 7, I could just write that as 7 times 5. That's fine. So that is justified, and the way I justify that is you could say real numbers are commutative. That's kind of fancy language, but you could even just say xy equals yx for real numbers. That's how you justify the switching of the order. And then how do I justify going from here to here? Well, that's that theorem again. If you don't like memorizing theorem 9.8, what you do in place of that is you put this fact. You just take that and put it in there. That's a fact. And then we're using that fact here as well. So that's it. It's a 3-step proof. Everybody can learn how to do that. Even if you just memorize it. It's short enough where you can just memorize the tick marks on a page and reproduce it that way, if that's what you want to do. Okay, so the first 2 proofs that I've given you are really, really straightforward. Those are the first ones you want to try. If you can't do those, then you don't want to try the third one because it's a little bit harder. So we want to prove that this fact implies, this is just some square matrix, and I'm just telling you that if I multiplied it by its transpose, I happen to get the identity. And then it has this fact that if we had this situation, then that means that the determinant of A is equal to plus or minus 1. Okay, well, we're really far removed from the result here. It's really hard to just look at that and just go, oh, duh. Obviously, if you had that, you'd have this. It's really hard because it's multiple steps. You're not supposed to be able to see that. So what we have to do is similar to this. We have to just sort of follow our nose. But look at what you're headed towards. We want to have the determinant involved. I don't know where this plus or minus is going to come from, but I got to get a number involved. Over here, I don't even have any numbers, but somehow I have to get a number involved. So you look through the chapter and you start to collect facts that seem relevant to this. So you might find facts that have transpose in it, because I see transpose here. So let's get some facts. There's theorem 9.1, which said the determinant of A is equal to the determinant of the transpose. I don't know how I'm going to use this, but I'm just collecting things that look like I might use them or they might be useful. We also had theorem 9.8 that says if you have the product of two, then that's the same as just doing the product of the determinants. So now let's start. And this is why you need some help. You need to watch somebody do these things, and then you'll be able to do them yourself. Okay, the first thing I'm going to do is I'm going to start with the left-hand side. Right, and now I need to do a set of logical steps that arrives at this as my last conclusion. I'm going to write it a little smaller so I can fit it. So I start with this fact. Well, the first thing I'm going to do is I'm going to take this here and I'm going to take the determinant of both sides. And the idea here is if A equals B, then that means that the determinant of A equals the determinant of B. Why is that true? Well, if A equals B, that means everything's the same. They're the same dimensions and every entry is the same, so clearly the determinant's going to be the same. Well, this is good because what's the determinant of I? What's the determinant of I? Let's go over here. If I is 1, 0, 0, 1, then the determinant of I is just 1. It's just 1 times 1 minus 0. And the determinant, remember I told you that the determinant, or the identity matrix behaves like the 1 in this world. So what it's going to be is that the area is going to be 1, or the volume is going to be 1, or the determinant is equal to 1. But you can just see that with a couple of practice examples. If I have the identity as a 3 by 3, its determinant is 1. Okay, you can even see it right away in your head. I'm going to do expansion along this column. So I'll go 1 times this determinant, and that determinant's 1. So it's 1 times 1, which is 1. Okay, so that's how I get the number involved. I don't know how it's going to be plus or minus, but I can say right now that the determinant of the identity is 1. So I have that so far. Now it's we're looking ahead here. If I could expose these and kind of get them by themselves, I have this fact that this guy is equal to that. So let's break this up into 2. I can break that up into A times A transpose equals 1. What's the fact that I'm using here? Well, it's theorem 9.8. That allows me to break it up into 2. You can just write in AB equals AB. That's the justification for that one. Well, now let's say that this is equal to A, right? Because we have this fact that the determinant of A is equal to the determinant of A transpose. So this implies that A squared equals 1, right? Because A equals A transpose. And now we can finally arrive at this conclusion, because if I solve for this, right, you just take the square root of both sides, I get the determinant of A, and I get plus or minus 1 over here. So that's the final conclusion there. We'll just write it right here. So my final implication is that A is equal to plus or minus 1. You put a little filled-in box that indicates that you finished your proof. You'll see that in math books and stuff. Maybe you learn QED or something like that. It's not necessary, but anyway, you can practice that. That's a slightly more advanced And you'll feel, you'll feel a sense of satisfaction when you can write that out. Take a clean piece of paper, see how far you get, look back at the solution, keep going back and forth until you can write the whole thing out without looking, and that'll solidify it for you. Any questions about any of those steps? Moving on to section 9.3. Here's where we find the inverse of a more general matrix, an n by n matrix. This is what all this work was moving towards. It's just we had to do the little detour and spend some time with determinant because it's a part of the inverse. The inverse of an n by n matrix. We already did 2 by 2. I'll remind you of that in a minute. But let's write down the general situation. So I have an n by n matrix. There's A, and I can write down its entries. It's A11, A1n. This goes all the way down. Now I'm in the nth row, first column, nth row, nth column. So there's the most general n by n matrix. I wrote them all down in the universe. Now, we've been calculating these cofactors, right? For every one of these guys, there's a cofactor, right? If there's A11, then there's C11. And if there's A12, then there's C12. So for every one of these guys, there's a cofactor. So I want to organize those in a matrix. That's what we do. We take information and we put them in a matrix. That's a natural place to store this. So I want to create what's called the cofactor matrix of A. Well, what should that be? Let's write some of the entries in. The entries should be, well, in the upper left-hand corner, I should have C11. And then that's the first row, first column. Then I should have the first row, nth column. Then the nth row, first column. And the nth row, nth column. So I'm basically just copying that, except with C's in it. That's what the cofactor matrix is. I can go calculate those. Each one of those is just a number. Now I want to introduce a new matrix, which is called the adjoint of A. And the adjoint of A is going to be the cofactor matrix of A transpose. Okay, so it's really this matrix, but I have to do that extra little step and to take the transpose. And the notation for this, we got to have notation, right? Because this is a little tedious to be writing all this down. Cofactor matrix of A. So we'll have this notation, adjoint of A. Let's go take a look at the 2 by 2 case. If A is equal to A, B, C, D, and let's go calculate the adjoint. Well, the adjoint's going to be, it's going to be the cofactor matrix. We can, let's just, for practice, that's C11, C12, C21, C22, and then I'll take the transpose. That's what it says to do up there. So I got 4 things to compute. These are not too bad to compute. Let's just remind ourselves that the negative 1 to the I plus j, that gives us plus, minus, minus, plus. Those are the locations. And so what is this going to be? When I do A, the cofactor is plus times, I cross that out, I get d. So let's just write a few of these out. So C11, that's equal to, it's negative 1 to the 1 plus 1 times the determinant of the matrix when I cross the first row and the first column out, so I just get d there. I get d in this spot. No, I get... yeah. Yeah, that's right. Sorry. Okay, so let's do this guy here, C12. That's going to be negative 1 to the 1 plus 2 times the determinant of the matrix left over when I cross off this row and this column. So I just get C in here. That's equal to negative C. I'm going to take the transpose. And then the other two you can compute. So this one's going to be minus B, and this one will be A here. You could write them in here if you like. C21 is equal to minus B, and C22 is equal to A. And then we'll take the transpose. So when I do the transpose, I make the rows into the column. So I have D minus C minus B A. Now, does that look familiar? Where have we seen where this was A and I switch A and C, or A and D, I switch A and D, and I make this one minus and this one minus. Isn't that where we had the inverse? Okay, so we're going to use that to get our general formula for the inverse. So A inverse, this was equal to 1 over AD minus BC times D minus B minus CA. What I have over there? And then we can write this in other notation now. This we now learned is called the determinant. I can write that down in my fancy notation. And then this guy right here happens to be the adjoint, right? See, I calculated the adjoint separately, and I got that. So I can say that this is the adjoint of A. And lucky for us, that's the formula for n by n matrices. So we can kind of use our 2 by 2 to see that that's the formula for the inverse for n by n. So a couple of things. First, I need to say that AD minus BC is not equal to 0. And then I'll say that the determinant is not equal to 0 here. Otherwise, the inverse doesn't exist. And then I'll say that this is the formula for n by n matrices. So let's put our formula to use on a 3 by 3 matrix. Okay, there's A, and we want to find A inverse. So what do we need? We need two things. In my formula there, you see I need the determinant, and then I need the adjoint. The adjoint is a matrix, and the determinant is a number. I need these two things. So let's first get the determinant. That's the determinant of 1, 0, 2, 3, negative 1, 0, negative 3, 1, 2. Okay, you can pick your favorite row or column. My favorite would probably be this column right here. Okay, so I've got 0 times its cofactor. Then I got minus 1 times the matrix left over when I cross off the second row, the second column. So that's 1, 2, negative 3, 2. And that's the first one here. Be careful when you start crossing things off because you might lose your minuses or something. For instance, you see I cross this off, it might hide the negative there. So be careful with that. Okay, this is actually a negative location. So it's plus, minus, plus down here. Sorry, it's minus. Got it wrong. It's minus, plus, minus. This is a negative location. So I'll put in a minus for that one. And then it's cross off its row, cross off its column. I have a 1, negative 2. Oh, that's not a negative 2. You see what I did there? See, I put that negative in and it's not a negative 2. Be careful. Okay, where am I at here? I have 1, 2, and then negative 3, negative 1, 3, negative 3, 2. Okay, look back up at the original one. So I'm crossing off this. And that's why I got it wrong there. Okay, so it's 1, 2, 3, 0. There we go. See if you believe that, because I've just done a bunch of things here. Make sure you believe me. Okay, I've got negative times 2 plus 6. Okay, it's 2 minus negative 6, so that's why I have 2 plus 6. And then minus 0 minus 6. So that gives me negative 8 plus 6, which is negative 2. Okay, that's just the determinant. Yes?
I have a question. Where did you get the negative from in front of 1, 2, 3, 0?
Okay, yeah, let's highlight that. Yeah. So I'm just trying to show you how you start to use shortcuts. So what I'm doing is I'm doing the expansion along here, right? Mm-hmm. When I do the cofactor, this one is a positive location.
Okay.
Because it's the 2, 2 location. Right. So this one's positive, and that means this one's negative when I do the cofactor.
Oh, okay.
So when I calculate I'm going to write it out now. So it's negative 1. That location is the 3, 2 spot.
Okay. So those negatives don't apply to the rest of the matrix? Like, don't you... I thought first you add in all the negatives or change all the signs where you need to change them, and then you do it. So
no, it's only when I'm doing the cofactor.
Okay.
It doesn't affect these numbers. These come from the original matrix. It's just the number in front that might be. So this negative right here is that negative 1, but I don't modify it because that's a positive location. Then this is a positive 1, but I do modify it because it's a negative location.
Okay, so you never change all of them. It's just like the row that you're using.
And only when I'm calculating the cofactor.
Okay.
Yeah. But let me finish writing this. So that negative or I did finish it. It's negative 1 to the 3 plus 2, which is negative 1 to the 5, which is negative 1. So that's why I have that negative there. That's when I'm calculating the cofactor. It gets a little tedious to write all these things out, so you want to develop some shortcuts. So I'm trying to, at first I wrote them all out, now I'm trying to do the shortcuts, so there's a little bit of a jump there. So feel free to ask. Okay, do we all believe that that's the determinant of that matrix? All right, I believe it. I guess that's what counts. All right, now we need to get this adjoint. So what I'm doing is I'm going to calculate the cofactor in every location. There's going to be 9 calculations here. Every single one of those guys, I have to go get the cofactor for each one. I want to make a distinction between calculating the determinant and getting the cofactors. When you're doing the determinant, you're multiplying these numbers times the cofactor. When you're just getting the cofactor, you're not multiplying by these numbers. That's a difference here. Here I multiplied by the negative 1 times the cofactor, and then 1 times the cofactor. When I go calculate that here, I'm not including that. the multiplication. I always see that on the midterms, so I'll mention it. Let's write in what we're going to do here. Now I'm going to calculate the cofactor, and what that's going to be is going to be the negative 1 to the I plus j, and then also a little determinant. So let's go put all the negatives in first. There's a negative here, there's a negative here, there's a negative, and there's a negative. Those are all the locations where there's going to be a negative. So now that part's done. Now what I need to do is write in all the little determinants from that original matrix. I'm going to reproduce A here so that I can look at it while I do it. Is that it? Okay. This is good practice. You know, sing along silently. Okay, the first one is I'm crossing off first row and first column, so it's this little matrix right there. I have the determinant of negative 1, 0, 1, 2. Okay, then I'm going to move over and I'm going to do I'm just going to take care of all the first row. So I just did first row, first column. Now I do first row, second column. I get 3, 0, negative 3, 2. Please follow me while I do this and tell me if I write something wrong. Then I'm going to cross off the third row, and I have this little block here. 3, negative 1, negative 3, 1. That's the first row. Okay, now we move on. Let's do the second row. Second row, I'm going to cross it off. Now I'm going to first do the first row with the second row. So 0, 2, 1, 2. So far, so good. Okay, second row, second column. That leaves me a 1, 2, negative 3, 2. Now the second row, third column. I need to be careful here. So second row, third column, I have 1, 0, negative 3, 1. Okay, now we'll move on to the third. I'm just going to reproduce it so it's clean. Starting here, so I'm crossing off the third row and now the first column. That leaves me with 0, 2, negative 1, 0. Then second column, so I have the 1, the 2, the 3, and the 0. And then the last one, home free here, 1, 0, 3, negative 1. Okay, let's just take a second here and let you copy it and see if you believe it. See if there's any errors in there. That's the adjoint. It's done. We just have to do those little determinants now successfully. Nine locations. Okay, the top left. Oh, and I forgot something. What were you going to say?
Isn't the second row, third column, 1, 2, negative 3?
Okay, this one right here?
Yeah.
Okay, so that comes from second row, third column, so 1, 0, 3, 1. Negative 3, 1. There's a negative here. You see it?
Yeah, I see it.
Okay. But I forgot something really important here. If you look back up here at the adjoint formula, it's the transpose. I forgot the T. Okay, we haven't done it yet, so we don't have to worry about it, but it's gonna, we have to take the transpose at the end to get our final answer. Okay, upper left, it's negative 2 minus 0. Then 6 minus 0. But then it's 6, but then there's a negative here. So that's negative 6. Then this is 0. 3 minus 3 is 0. This one is 0 minus 2, but then there's another negative, so it's positive 2. This one is 2 minus 6, so that's 8. 2 minus negative 6. 2 minus negative 6 is 8. And then this one is 1 minus 0, but then there's a negative in front, so it's negative 1. This one is 0 minus negative 2, so positive 2. 0, minus 6, but then with a negative, so it's 0, minus 6, negative 6 with another negative, so positive 6. And then this one's negative 1. Okay, so finally we can take our transpose now. I have 2, negative 2, negative 6, 0, 2, 8, negative 1, and then 2, 6, negative 1. That right there is the adjoint of A. So it's a lot of work, but I challenge you, see if you could take A and just write this down. Could you do that in your head? You can, I mean, if you really concentrate. It takes a lot of concentration. But that'd be a good challenge for you. Even if you could just write this one down, that'd be good. And then see if you can see the determinants that you're supposed to take as you cross them out with your mind. That's really good practice for your just brain strength. Well, it seemed like we're kind of sidetracked here. Remember, our goal was to find the inverse. We went and got the determinant, we went and got the adjoint, so now I can write down the A inverse. That's equal to 1 over the determinant times the adjoint of A. So I have negative 1/2, that's 1 over the determinant, times the adjoint, that's this one, 2, negative 2, 2, negative 6, 8, 6, 0, negative 1, negative 1. And then we can incorporate the negative 1/2. I have a 1, negative 1, negative 1, 3, negative 4, negative 3, 0, 1/2, 1/2. That's A inverse. And I invite you to multiply this matrix times the original matrix and see that it gives you the identity. And maybe even try that in your head. Be good practice. Phew, I got the answer that I have on my page. Okay, any questions about that? I don't do too many examples of this, and I think you can appreciate why, and you can also appreciate that I don't. So, that's just, we're not going to have to go beyond a 3 by 3. That's too much, because then we'd have to do 16 3 by, if it's a 4 by 4 matrix, we'd have to do 16 of those cofactors, and each one of those is a 3 by 3 matrix, so it's too much. This is the most that you really have to be responsible for, even though the formula is true. Now, the nice thing about this too is that if I ask you on the midterm, and I will, here's A, find the inverse. When you get your answer, why don't you at least mentally make sure that it is the inverse? You can always check your answer. Okay, so don't just write it down. You can always multiply and see if you get back to the original, or if you get the identity when you multiply. All right. So what we're going to do now is, I've done a lot of math. I've got a lot of machinery available to us. What I'm going to do is we're going to look at an economics example where it uses a lot of the stuff that we've been talking about. I'll basically have 2 or 3 economics examples that you have to be responsible for. One from the first part of the course, which is this part, and then one later on. So I'm not going to focus on it, but there are a couple examples that we're going to have. And this is also just a little break from the dry mathematics. Does anybody know this guy? Lantief? He's an economist. He won the Nobel Prize, and what he did was he studied the economy, the industry sector, and what he realized is that if you're in one particular industry, you use all the things from the other industries. So as an example, what are the basic raw products? We've got things like electricity and water and timber and maybe iron. There's just, and then there's different people out there producing each of those. But let's say I want to produce iron. Well, I'm going to need some electricity. I'm probably going to need some timber to build myself a building. I'm probably going to need some water, right? So when I'm involved in one aspect of an industry, I'm going to need something from all the other industries, and so they're interrelated, and then that creates some complexity. And so, how do you study that? So this guy decided to study, and in fact, I think what he originally did was 50 different things from the industrial world, 50 different things, and each one used all the others. Maybe some of them didn't, but what that created was a 50 by 50 matrix. Now, in order to understand what he did, we have to simplify it and just do 2 by 2. Okay, so we'll just have this is a model. It's a 2 industry model. When you see this word a lot in economics, think about what it is. What is a model? It's it's a simplistic version of something that you see in the real world, right? If I want to build a boat model, I have the real boat, but then I scale everything down and I make a miniature version of it. So when an economist looks into the real world and finds something he's interested in, or she, this guy saw that this particular aspect of the economy interesting to him, so he started studying it. And what you want to do is you want to create something so that you can predict what's going on in the real world. And that's what a model does for us. It's a simplistic version of the real economy, but it reveals some aspect of it and it allows you to predict. That's the goal. Okay, so in our 2 industry model, we're going to simplify. We're just going to have electricity and water. And just for lack of creativity, I'll call that E and W. So what do we want? If we're going to produce the electricity and the water that's necessary for society, you see, it's hard to store electricity and store water to be used later. So to be really efficient, I'm going to want to produce the exact amount that I need. That would be ideal, right? So let's figure out how to do that. So what we want our output to equal the demand. Okay, I know that there's a certain population out there, they're going to need some water, they're going to need some electricity, and through the historical records I can figure out what they're going to need. So then that'll tell me how much to produce. But not quite, because the demand, you see, there's the amount that the population needs, but then there's the amount that I'm going to need in order to produce it. That's the whole point of this land to model, is that if I'm going to produce electricity, I'm going to need both electricity and water to produce it. So I might say, so the society might need 1 unit of electricity, but if I only produce 1 unit of electricity, it costs me something to do it, so I'm not going to end up with 1. So I have to create a little bit more in order to have 1 for the society. So that adds a level of complexity, but we can handle it. So this demand, it gets broken into 2 parts. There's the internal demand and the external demand. This is from the population. Those 2 things equal the demand, and then I want that to equal the output. Now I have to spend a lot of time to explain all these things and set up the notation and stuff, and that's why I don't do too many of these economics examples in class, because they eat up a lot of time. But when you're calculating this at the end, it doesn't take as long once we have the setup. Okay, so this is from production, and this is from the population. Let's assign some variables now. Okay, so $1 of electricity, it needs, and these are just numbers I'm giving you, so you have to have something to be given in the problem. So $1 of electricity needs 30 cents of electricity and 10 cents of water. And if I'm going to produce $1 of water, then I'm going to, this is all my internal demand, I'm going to need 20 cents of electricity and 40 cents of water. These are all cents here. Okay, and then let's take a look at the external demand. The external demand, so let's say the population needs $12 million worth of electricity and $8 million, those are the numbers I have, yeah, of water. So we're going to have 12 million of electricity and 8 million of water. And let's start to organize this information, because here's we're going to start using all the matrix mathematics that we've been studying. So I'm going to collect this. My demand, D, okay, it's the demand for electricity and it's the demand for water, but I can just write that. I know what those numbers are. It's 12 and 8. So there's my demand vector, external demand vector. And then how about the output? Output is, let's call that, let's say x1 is equal to the output of electricity, and x2 is the output of water. And let's organize that in the same way. I have my x is my output, and then it's a vector consisting of the two things that I'm interested in calculating the output of. So x, that's equal to x1, x2. My goal here is to solve for this x. I want to find out what the output that I should have from the plants in order to satisfy the internal and the external demand. That's the goal. Okay, last thing, we need to organize this information in a matrix. Okay, we did that for the other two things. Let's put that into a matrix. And we have a name for this. This is called the technology matrix. This is the thing that was studied by Lantief. And like I said, he had a 50 by 50, I think. That's what my memory is telling me right now in this moment. Okay, what is this guy going to be? Well, on this side here, I'll have the input of electricity and water, and up here I'll have the output. That's why it's called an input-output. That's what input-output analysis. So here I have electricity and water. So what should I put in here? Well, I've got 4 pieces of information. Here's the amount that I need from electricity to make electricity, and here's the amount from water that I need to make $1 of electricity. So if I want to make, let's write it out in English here. So this is the electricity needed for $1 of electricity. And then this guy will be the water needed for $1 of electricity. So this is all the $1 of electricity, and this is the water needed for that. Oh, excuse me. I got it. This is the input here, E. So this is the electricity needed for $1 of electricity, and this is the electricity needed for $1 of water. So the whole top row is electricity needed. And then this whole bottom row is the water needed. So this will be the water needed for what? To have $1 of output of electricity. And then this is the water needed for $1 of water. Okay, so you see how the matrix helps with that, because I'm pairing up electricity and electricity. I put that number there. And then I have electricity and water, water, electricity, water, water. Okay, so let's put those numbers in now. We have those. I need 30 cents of electricity for $1 of electricity. And I need 10 cents of water. That goes down here for $1 of electricity. And then 0.2 and 0.4. And we'll call that M. All right, so anyway, that's 3 panels there just to set up the whole problem. If you're given a problem like this, you just immediately start writing down the vectors. It takes a few seconds, but you have to have the setup first, so that's what we spent all our time on. Okay, now let's solve the equation. So we start with this principle that the output equals the demand. And how do we get the output? The output we've labeled as X. So that's X. And then the internal demand, depending on how much output, I multiply it by that matrix. That matrix tells me how much I need to spend on each type. So the internal demand is going to be Mx, and then I have the external demand. And this is the internal. And this is the external. Okay, now we get to use our mathematics. See, so this guy looked out into the world, he saw this phenomenon happening, he tried to describe it, he tried to organize the different things. Okay, there's demand, I got a vector for that, I've got output, I got a vector. He's just setting up the model to describe what he sees in the real world. But now the whole goal is to solve for X. So here's where you need the mathematics. Now let me ask you, if I have, let's go over here and do this. If I have, let's say I have X equals Mx plus D. Let's just go back to our high school situation. How would I solve this? Well, I'd go X minus Mx equals D. And then what would I do here? If this was a number, I'd combine them, but when they're like that, the best I can do to solve for X is to factor it out. So that's 1 minus M, X equals D. So then if I want to solve for X, X is equal to, well, how about 1 minus M inverse D? We usually would just write 1 over that, but I want to write it specifically like that because now we're going to translate that into matrices. When I solve this matrix equation, I want to do it the same way. So let's say that implies that X minus Mx equals D. And then I want to do this same step here where I factor out an X. See, there's an X in both terms. Remember, when I multiply this out, I need to get back what I started with. So the question is, what do I put right here? Over here, we got a 1. So what plays the role of 1 in the matrix world? The identity matrix, yeah, the identity matrix. That plays the role of 1. If you like, you can write a little I right here, and then you can see the factorization. Because remember, the identity times anything just gives you the thing back again. That doesn't change it. All right, so then now I could say that X is equal to I minus M inverse D. And then we can go calculate these things. So I minus M, that's equal to 1001 minus M, which is 0.3, 0.2, 0.1, 0.4. Let's get that. That's 0.7, negative 0.2, negative 0.1, 0.6. And then I minus M inverse. That's just the inverse of a matrix. We know how to do that. I need 1 over the determinant. That'll be 1 over 0.42 minus 0.02. Because I'm doing 7 times 6 is 42 with 2 decimal places. Then I'm doing 2 times 1 with 2 decimal places. That's how I get that. And then what do I do with these guys? I switch them, so 0.6, 0.7, and then I make those positive. See, we're using our math here, right? Once we get the economics model, we're using our math. And then I can just tell you what this is. Okay, this here is 1 over 0.4, which is 1 over 4/10, which is 10 over 4. So let's just write that out so you can see that. It's 10 over 4 times 0.6, 0.2, 0.1, 0.7. I mean, you can just use a calculator too for this if you like. Not on my exam, though. Okay, so the reason I wrote that here is, see the 10, it gets rid of all the decimals. Just pretend the decimals aren't there. That's the 10. And then I'm going to divide everything by 4. So I get 1.5. This is 3 halves. Then it's 1 half. And then 0.25, it's 1/4. And then 7 over 4 is 1.75. Okay. And so we're home free now. Our whole goal was to find x. So x is equal to that matrix times d. If you want, we can put a grid here so you don't lose track of those numbers. And d was 12 over 8 over there. So x, the amount of water and electricity that need to be produced in order to satisfy the demand of the public, I have to do more than the 12 and the $8 million worth that's needed, because I'm going to use some when I produce it. And the amount that I'm going to get is 22, I have it right here, 22 and 17. Okay, when I do this multiplication, 1.5 is 18 plus 4 is 22, and then 1/4 of that is 3, 1.75 of that is 14, that makes 17. So 22 million of electricity is needed, and $17 million worth of water in order to produce the amount that the people need. So there you go. You still want to study economics? You guys are all econ majors. I don't know, how many of you have seen this stuff before? I think you might have to, you might, it depends on the teachers you've had. Some of you have seen it. Yeah.
Sorry, why did you multiply by 2 over 8 that?
12 over 8.
Yeah, sorry, 12 over 8.
Yeah, okay, so see x up there, when I solved it, I got x is I minus m inverse d. Then I went and worked and found out what I minus m inverse is. I got this matrix, and then this is d.
Oh, okay.
Here's d right here. Yeah. Any questions? Yes.
On the midterm, are we going to have an economics problem? Or is it just all
Yeah, probably. But you see, like I said before, I spent a lot of time explaining all these things. So if you got a problem, I would just say, here's the demand, 12 and 8 million. And then find the output with this technology matrix. I'll just give you the matrix. I'm not going to give you this big word problem and make you sit there and read it and everything. I'll just give you the whole setup. And then what you'll basically have to do is this equation here, because I just want to make sure you can do the math. This is a great comparison or a great example of what we're really doing in this class. You learned how to do this when you were younger, and you did not learn how to do this. This is big boy equations, right? We've got matrices rather than numbers. It's a much higher level. So that's really what I need to test you on. So I could even do it without the context. I could just give you a matrix and say, solve this equation. I could do that too. And I've done that in the past. Well, something from this will be on the midterm. You should start getting nervous about the midterm. It's a week from Friday. I'm nervous about it. I'm always nervous that I have typos on my midterm, so I do get nervous. Yes?
I forgot how you, like that step right before you go to 17, about the operation of that word.
Point to me where you're. Where you,
Just about the result, the answer.
here.
Yeah.
This is.
From there, yeah.
Yeah, okay, so what I'm doing, I'm just doing matrix multiplication. So I just take the 12 and the 8, put it on a side, and then I go 12 times 1.5 plus 8 times 0.5, that gives me 22. Then 12 times that plus 8 times that gives me 17. Yeah, it's just matrix multiplication. So you see everything we have here. We got multiplication of matrices, we got inverses, I had to have a determinant, right? Everything that we've done is pretty much in this problem. So I like that. What we're going to do right now is we're going to solve every system of linear equations with n variables and n equations. So the same number. We got to have, that's key. We got to have the same number of variables as equations. We're going to solve all of them in the universe that have unique solutions. So we're going to do a little bit of theory. It's going to have some notation and stuff. But at the end of it all, we'll get a nice computation that we can do. Okay, so here we're going to start with given any system of n linear equations. This is kind of the culmination of everything that we've done. We started the class by studying systems of linear equations. Then we sat there and we practiced row operations. Then we went from there and we just studied matrices by themselves. Now we're coming back and doing systems of linear equations again and putting it all together. That's what Kramer's rule does for us. So I've got n linear equations, so you just want to picture a whole bunch of a list of equations. And then I have to tell you how many variables with n variables. So these are the same. This is a special case. We've got n equations and n variables, and what that gives us is a square matrix. So that's key. You can't do Kramer's rule unless you're going to get a square matrix. Okay, let's write it down. Let's So what would we do? If I had a list of n equations with n variables, what I would do is I would grab all the coefficients and put them in a matrix. And then I would grab all the variables and I'd put them in a little vector and I'd call that x. And then on the right side of the equation, I would have a list of numbers. I'm going to call that b. Well, that's not very satisfying because there's, it's like I've said before, this is like an icon on your desktop. You got to double click it and there's a lot of stuff inside of this. This is a very compact way of writing it, but it's true. I have a matrix times a list of variables equals a constants. A list of constants. Okay, well let's expand it a little bit. We'll double click on that. If I double click on it, what do I get? I get a bunch of coefficients, and I'm going to write them out because I'm going to be careful about this. The first one is a11, the next one is a12, then I have a1n. Then I go all the way, I guess we could write that. I'm not going to do it right away. Then I go all the way down. This is the nth row, first column, nth row, second column, nth row, nth column. And then x, that's a list of n variables, so x1 through xn, those are the variables. And then on the right side, I've got b1 through bn. So we're going to solve this equation. And the power of that is that we're going to be solving all infinitely many linear equations with the same number of variables in the universe, all at the same time. We're going to get a nice formula. It's going to take a little bit of work, though. Okay, first thing I want to do is I want to make a little special matrix. So you're given A, that's the coefficient matrix, and I'm going to make a new matrix from it. And what I'm going to do is A sub j, why would I call it J? Just think in your mind, where else have we used the letter J? What do J's describe? No? It's the other one. it's I by IJ, right? The J's have been the columns so far. So I'm going to do something with the jth column. That's what that notation implies here. Okay, something with the jth column. Although that would be a good guess with the rows too. All right, so what am I going to do? This is the matrix obtained from A. That's why we use that A notation, right? Having the A here implies it comes from the original A. Then A sub j, it's the matrix obtained from A by replacing the jth column with B. So that stuff on the right side, I'm going to take that and I'm going to put it in the jth column. Now, there's n of these I can make. I can make A1 and A2 and all the way up to AN. And every time I just take this and I just put it in place of the column, the jth column. Let's get a little picture of it. So A sub j, that's going to be A11, A12, and then I'm going to have B1 through Bn, and then A1n. And then this guy goes all the way down to AN1, AN2, ANN. And this is the jth column. So I literally just remove the jth column and then put in place of it whatever I have over here. Just for fun, let's go calculate, let's go get one of these guys. Okay, just for practice, let's get A1. Okay, that should be the easiest one to get. What we're doing right now, you've probably had enough experience in school to know that once in a while we go off and start doing this theory, and then eventually you arrive at the formula, and then that's what you need. So I always attribute this as, when I was in school and I saw this, I knew at the end I'm going to get a formula, so I don't necessarily have to write all this stuff down. It's just, maybe just let it wash over you, and then at the end you'll get the formula. Because what this really is this is just an opportunity to get a little mathematical maturity and just deal with this. So if you just sit there and you just copy it, chances are you're not going to get much out of it in this moment. And then, how many of you go home and read your notes when it comes to this stuff? So you sat there and watched it and copied it down, didn't get much out of it. Then to make up for it all, you don't read your notes, right? So maybe just watch it for a little bit. It's like a mental mechanical bull ride. So, I start here, get the bull going, and you just see how long you can hang on. At some point, everybody loses it. That's okay. You should just understand that's part of the process. Okay, let's just get one little example here. Let's go A1. Let's see if we can get A1 out of all that. So what is A1? I take A and I replace the first column. So I'm going to put B1 through Bn in the first column. And then everything else has to stay the same. It's going to be A, this is the first column, first row, second column, first row, nth column, nth row, second column, nth row, nth column. So there's A1. We did it. I replaced the first row with B. Let's also get the determinant of this. Ew. Let's get the determinant. And when I do this determinant, I'm going to expand along the first column. So what is that going to give me? It's going to give me B1 times the cofactor C11 plus B2 times the cofactor, well then when I go down here this is C21 because that would be the second row, first column. And then so on all the way down to the last one, B sub n times Cn1. That would be the determinant if I expanded it along that first column there. And what I want to point out here is that these cofactors, these are the same ones from A, because notice when I go to calculate all these, I'm always going to cross this off, and so all the numbers that are left over are all from A. So these are the cofactors. These are the same cofactors as in A. Just see if you can believe that. Right? Aren't all the numbers that I use to calculate those cofactors, aren't they just all the numbers from A? The B's don't really show up. They show up out here, but not when I calculate these things. Okay, still on the mental mechanical bull? Hopefully. We're almost there. The power here, though, is we're going to solve all of these in the universe. So that's great. Okay, let's do it. Let's solve every one in the universe. AX equals B. Well, let's assume A inverse exists. So that has to happen. Okay, we've got to have a situation where the inverse exists, because then I can solve for x. If the inverse exists, then I know that x is equal to A inverse B. We've seen that a little bit already. So I'm going to multiply on both sides by A inverse. But we know the formula for A inverse now, so let's write that out. What's A inverse? That's 1 over the determinant of A times, that's how much do I want to write in here? A lot. Times the cofactor matrix. Let's write it out, the formula first. So this is times the adjoint of A, all times B. So A inverse, that's just this part right here, times B. And that's 1 over A times, okay, let's write down what this adjoint is. It's C11, C1n, Cn1, Cnn. Those are all the cofactors, and then I take the transpose times B1 through Bn. So what we have here is x. Okay, what happens if I take, let's do the transpose now. Let's do, so it's 1 over A. Then I do the transpose. We're almost at the end here, so just hang on. Okay, what happens when I do the transpose? All of this stuff becomes the columns now. So I get C11 all the way down to C1n. That's different than this one, Cn1. And then I have, this is C12. And then this is C21, Cn1, and this is Cnn. Okay, we're ready to go. So here's what I want you to see. Let's just calculate x1, okay? How do I get x1? I'm going to multiply out the top row here with b. Can you see that? That's how I would get x1. I would multiply this out, right? And that would give me the very first location of my new matrix. Can you see that? So let's write out what x1 is. x1 is equal to 1 over the determinant of A times, okay, I'm going to go B1 times this, plus B2, that's the next one, times this guy, C21, plus dot dot dot, plus Bn times the last one, Cn1. Okay, you believe me? You see that anywhere else on the board? How about up there? Isn't that the determinant of that special matrix A1? So I could rewrite this another way, right? I could say this is x1 is equal to the determinant of A1 over the determinant of A. You see, this thing right here is the same as that up there. Okay, so now, is there anything special about x1? What if I had x5? What do you think that would be? See, look, I have x1 and I got a1. It's not a hard leap to realize that x5 or x10 is going to be a10 over this. Or in general, I can write down what's called Kramer's rule. And that's x sub j is equal to the determinant of a sub j over the determinant of a. Okay, so given any system of equations, as long as the inverse exists, if the inverse exists, that means the determinant isn't 0, so it's okay to divide by it. This gives me every variable in the list. If I want x5, I go determinant of a5 over determinant of a. If I want x3, I want a determinant of a3 over determinant of a. And it's a nice formula for all of them. Okay, so that's it. That's the culmination of everything. If you were sleeping, you should wake up now because I'm going to do some examples along these lines. Let's start with, how about, how about 2x equals 3? That's a system of equations. So x, that's the only variable, so that should be equal to the determinant of a1 over the determinant of a. Well, okay, what's a? A is this, right? This is the a right here. This is a x equals b. In this case, A is just a 1 by 1 matrix. We'll do I should put the determinant there. And then what's A1? That means I take B and I replace the first column of A with 3. But there's only one column to begin with. So that's the determinant of 3, which is 3/2. Okay, so it's kind of silly to do it that way. Obviously, you can just do this in your head. But you see, Kramer's rule still works even for this case, where we have a single equation with a single variable. It still works there. Well, that gives us hope. At least, it's mathematics, right? It works wherever you define it. If it doesn't work in a certain place, then it's not called mathematics. All right, here we go. Now let's do I think I have here we go. So let's do x plus y and x minus y equals 1 and equals 3. Here, I'll tell you the solution. The solution is xy equals 2, negative 1. So you can practice on your own if you want. Well, according to Kramer's rule here, let's say x is like x1 here. So what I'm going to do is I'm going to take the determinant of the matrix where I replace the first column with the right side and then divide it by the coefficient matrix. So let's write that out. So you see it. X, I'm considering that the first variable. It's like x sub 1 if you like. If you want to replace them with x1 and x2, that's fine. Okay, so x, how do I get that? That's going to be the determinant over a determinant. This guy here is just the coefficient, so it's 1, 1, 1, negative 1. That's the determinant of A. And then the determinant that goes here is I just put the 1, 3 in the first column. I put the 1, 3 here, and then I keep the 1, negative 1. So that's equal to negative 1 minus 3 over negative 1 minus 1. So that's negative 4 over negative 2, which is 2, which is our answer up there. And then y, that's equal to, okay, it's going to be a determinant over a determinant. The bottom determinant is going to be the same, because it's just the coefficients. See, that's always the same. What changes now is I now take the 1, 3, and instead of putting it in the first column, I'm going to put it in the second column. And I leave the rest alone. So now that's 3 minus 1 over 1 minus negative 1 minus 1. So that's 2 over negative 2, which is negative 1. So there's our solution. That's not to say that you couldn't have done this one more easily just using your high school methods, but we're just practicing it so you see it on a 2 by 2. I did a 1 by 1, then we do a 2 by 2, and then finally we'll do a 3 by 3. We don't really do 4 by 4s because, again, we're going to have to do, like we could, but it'd be a lot of 4 by 4 determinants. So let's do a 3 by 3 and call it a day. x1 plus x2 minus 2x3 equals negative 1. And 2x1 minus x2 minus x3 equals 4. Minus x1 plus 2x2 plus 5x3 equals 1. And I'll give you the solution. So you can work towards it yourself. Let me make sure I copied it right so I don't get a disaster here. Okay, I'm ready to go. So I've got to compute 4 determinants. That's what I need A. A is going to be on the bottom of every one of them, so I need A first. Let's go get the determinant of A. That's going to be the determinant of 1, 1, negative 2, 2, negative 1, negative 1. Now when I do this, I could reduce it, but I'm just going to go along the top row in each case. You can just do these 3 by 3s by brute force. Okay, so remember this is a plus location, that's a minus location, and a plus location. So this guy is equal to, it's 1 times, I'm going to write it out so you see it. So it's 1 times the matrix left over, which is negative 1, negative 1, 2, 5. Then minus 1, that's this minus right here. It's a little tricky. Times the determinant of 2, negative 1, negative 1, 5. And then minus 2 times the determinant of 2, negative 1, negative 1, 2. So let's see if I have that all the same as... Nope. What did I do there? I copied that one wrong. This one here. Oh, no, I didn't. I'm looking at the wrong one. That's right. Everybody believe that? I believe it. Okay, so that's equal to negative 3 minus 9 minus 2 times 3, which is negative 18. Okay, see if you believe that. That's the first one because we need that one in order to compute all the others. Now I've got 3 more to go. All right, A1 will be the determinant. Okay, now I'm taking that original matrix, but I'm putting the right side in, that negative 1, 4, 1, and that's going in the first column. And the rest of it's the same. 1, negative 1, 2, negative 2, negative 1, 5. Okay, that's equal to, I'm just going to write these things out just to save some time. Again, I'm going along the first row. So that way, the plus and minuses are always the same. It's plus, minus, plus. So that minus is that second minus there. And then, of course, see if you believe me while I'm doing it. Okay, that's the cofactor expansion along the first row. And that's equal to 3 minus 21 minus 2 times 9, which is negative 36. Okay, then A2. Okay, now for A2, I'm taking that B and I'm putting it in the second column. And then everything else stays the same. So I have 1, 2, negative 1, and negative 2, negative 1, 5. And that's equal to 4, negative 1, 1, 5. I'm going again along here. Just keep it the same every time. Plus 2, negative 1, negative 1, 5, minus 2, 2, 4, negative 1, 1. And that gives me 21 plus 9 minus 2 times 6. And that's positive 18. So again, see if you believe that. And then A3. Now I'm taking that B there, negative 4, 1, negative 1, 4, 1, and putting it in the third column. The rest stays the same. And I'll go along the first row again when I do this. So I get negative 1, 4, 2, 1, minus 2, 4, negative 1, 1. Okay, this guy is negative 1 minus 8 is negative 9. Then 2 minus negative 4, that's positive 6, but then I got a minus out front, so minus 6. And then 4 minus 1 is 3 with a negative. So that's negative 18. And we're home free. Those 4 matrices are everything I need in order to get the 4 variables, or the 3 variables. Okay, so now x1, that's a1 over a. So that's negative 36 over negative 18, which is 2. x2 is the determinant of a2 over a. That was 18 over negative 18, yeah, which is negative 1. And x3 is a3 over a. That's it. That's your solution. So it comes down to 4 matrices. Now I'll tell you that you may prefer to do this a different way and you still get the same answer, and that's fine. I'm not going to put you in a position where I say you must use Kramer's rule. I'll probably just give you a system and you can have the choice. However, if I decide to make the answers fractions, you're going to want to use Kramer's rule, because imagine that the answer was 14 over 27. Then that's just for x1. Let's say I had 14 over 27 for this. Well, that would have meant that this is 27 and this was 14. And that didn't require any fractions, because I just got a 14 for that, and then I got a 27 for that. And the answer is a fraction, but that would have been nasty to try to do row reduction to solve it. So it does have its advantages. Also, they can program computers. You can program a computer to do this. Right? Put in 10 variables, 10 equations, tell the computer to do these determinants. And that's how you program a computer for solving these systems of equations. So it does have a little advantage when you have fractions and things like that. Also, what if I just said, here's a system of equation with 4 variables, go find me x3. I don't need all 4 of them, I just want x3. Well, then in that case, it would just be 2 determinants. So, you know, Kramer's rule does have its advantages. I could give you a 4-variable system and just say, go find me x3, and that would just be 2 4x4 determinants. And, and even if the answer was a fraction, you could get it fairly simply. Okay, that's enough for today. Yeah?
How you're doing A1, 2, and 3?
Yeah?
So you were just switching so for A2, you were just switching the second column to the first part?
No. No, you're saying, did I switch these two? I know it looks that way, but what I'm really doing is I'm taking that B there, right, the negative 1, 4, 1, and I'm putting it in this matrix in the second column. That's what, and then for here, I'm putting it in the third column. And here, I'm putting it in the first column. That's how I make A1. That means take the thing on the right side, the constants on the right side, and put them in the first column. This one's take the constants on the right side, put them in the second column, then the third column. That's how we do it.
Okay, but the signs still say the same, right? Just plus minus plus.
Yeah, because when you're doing the determinant, it's just the locations. Yeah, the same locations. Yes?
So why did you circle the first row?
Because that's the row I'm using to determine, to get the determinant.
So you could just any, right?
I could. I did the same one so just to keep it a little simple. Because I wanted to have the same plus minus, just so that I didn't have to deal with that part.